Okay, in this video I'm going to go over section 10.4. It's going to be working with power series, and so I'll show you a couple examples and kind of problems that essentially use limits or evaluate limits and integrals and other things using the power series expansion. So let's start off with this example here. It's a limit. So I want to calculate the limit as x goes to infinity of this function, x times sine of 1 over x. So if you remember from Calc 1, if I would kind of plug in infinity, right, I would get infinity, and then I would have times sine of 0, which is 0. So this is known as an indeterminate form, right? So I could manipulate this thing and use L'Hopital's rule to evaluate this limit, but I'm actually going to use the power series expansion for sine to actually evaluate this limit. So from table 10.5, we know that sine of x can be represented as the infinite series. Let's see, k equals 0 to infinity of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1 factorial. Okay, so so if this is sine of x, all we're really going to need to evaluate this is the first few terms of this guy. So if I plug in k equals 0, we get x. If we plug in k equals 1, we would get negative 1 times x cubed over 3 factorial. Then we would get plus x to the 5th over 5 factorial, and blah, blah, blah. So what we're going to have here is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus some other terms. So in my limit that I'm evaluating, it's not sine of x, right? It's sine of 1 over x, but I can write sine of 1 over x as sine of x to the negative 1. So sine of x to the negative 1, right, using this expansion would actually just be wherever you see an x, right, in the original series, you would put an x to the negative 1. So this would be x to the negative 1 minus x to the negative 3 over 3 factorial plus x to the negative 5 over 5 factorial, and so on. And so now I have sine of x to the negative 1, but I want this x here, right? So I'm trying to develop the series for this expression overall. So x times sine of x to the negative 1, right? That would be x times x to the negative 1 minus x to the negative 3 over 3 factorial plus x to the negative 5 over 5 factorial plus blah, blah, blah. And so x sine of 1 over x times x to the negative 1 is 1. Here I would get minus x to the negative 2 over 3 factorial plus x to the negative 4 over 5 factorial and plus a bunch of x's that are in the denominator. And so one last step, right, if I want to do the limit as x goes to infinity of this expression, notice that this would be the limit as x goes to infinity of this infinite polynomial here, which would be 1 minus 1 over 3 factorial x squared. So I'll put the x down in the bottom here, the x squared and the x to the 4th. And if I was to guess the next term, it would be 1 over 7 factorial x to the 6th, right, and so on. And so when I evaluate this limit, right, all of these terms are going to go to 0 because they're blowing up in the denominator. All I'm going to be left with is that 1. So this limit is 1. So this is a way to evaluate the limit using a power series expansion. All right. We can also use a power series expansion to evaluate an integral. So just like before, right, we have sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay, so I'm using the same exact expansion for sine from table 10.1, 10.5, sorry, right? So now I can evaluate sine of x squared. So sine of x squared is equivalent to, wherever I see an x, I would replace it with an x squared. So this would be x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial plus, minus x to the 14th over 7 factorial and blah, blah, blah. So if I wanted to do the integral from 0 to 0.2 of sine of x squared dx, I can do the integral of the first couple terms, and this will give me a good approximation. In fact, I'll be able to approximate it to 4 decimal places by only doing the first couple terms. So I would do 0 to 0.2 minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus blah, 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 and then dx. Okay, so I'm really evaluating integral of an infinite polynomial here, but you'll see that I really only have to do a few terms. Now, why are we doing this, right? So the motivation here is that it's very difficult to find, or maybe even impossible, to find an antiderivative of this thing, right? I can't use u sub, I can't use integration by parts, right? If there was an x here, I'd be able to use u sub, but I can't do it, right? It's not there. So here our next best solution is to replace it with a power series and try to use this as our next best guess. So the antiderivative of x squared, that would be 1/3 x cubed, right? This would be 1 over 3 factorial times 7, x to the 7th, plus 1 over 5 factorial times 11, right, x to the 11th, minus 1 over 7 factorial times 15, x to the 15th, right, plus blah, 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 evaluated from 0 to 0.2. And so when I plug in 0, all these terms are going to go to 0 because they all involve an x. But my integral, right, this represents an area, right? So this function between 0 and 0.2 might look something like, I don't know, that. And if this is 0.2, what we're trying to evaluate here is the area, right, under that curve from 0 to 0.2. So we know that this thing exists, right? It's a finite number. So this series must converge. And in fact, it's going to converge to something, right, close to whenever I plug in 0.2 here. We'll just take the first couple terms to get a pretty good approximation. So I would have 1/3 times 0.2 cubed minus 1 over 3 factorial times 7 times 0.2 to the 7th plus 1 over 5 factorial times 11 times 0.2 to the 11th minus 1 over 7 factorial times 15 times 0.2 to the 15. Okay? So this is an alternating series, correct? So if you remember back when we talked about alternating series, right, we can get an idea of what this series converges to, and say one of these terms is like 10 to the negative 7th, then that kind of gives me an upper bound on the error. So I'll just calculate the first 3 to see what the value is. So we get, let's see, 0.2 cubed divided by 3. So the first value here is 0.00267 minus 0.2 to the 7th. Let me just do 0.2 to the 7th divided by 7 divided by 6, because that's 3 factorial. And look at that, we already get minus 0.12345 3047. So I'm not even going to compute the next two terms, because this, right, already has 6 zeros, so it's already within 4 decimal places. So I'm just going to circle this one and say, hey, this is good enough up to 4 decimal places, because this is not going to change those decimals. All right, so this area is approximately equal to 0.00267. We can also start with a series and ask, okay, what function has this power series? So a lot of times, right, you have to make this thing look like a variant of one of the series that are on table, that's on table 10.5. So notice how -1 is raised to the k, x is raised to the k, and 3 is raised to the k as well. So I could put them all over the same thing raised to the k, which would be -x over 3. Right? So this series is equivalent to this, and if we remember, 1 over 1 minus x is equivalent to, right, k equals 0 to infinity of x to the k. And this is true for the absolute value of x less than 1. So remember that one theorem that said, right, if I have a function here, like 1 over 1 minus f of x, I can formulate its power series by replacing x with f of x. So that's exactly what we have here. So f of x is actually this thing right here, right? So this series must be equal to 1 over 1 minus negative x over 3, because that's f of x. And so this thing is equal to the function. Now, what would be the interval of convergence? Since x must be less than 1, the absolute value, here the absolute value of negative x over 3 must be less than 1, which means the absolute value of x over 3 is less than 1, which means the absolute value of x is less than 3. So this would be that thing's interval of convergence. Right? So here it's kind of just working backwards. Last thing, we can also now determine, say I have an irrational number such as ln of 3 halves. We can actually determine the series that converges to that number. So I'm going to, since this involves ln, I can look at the series ln of 1 plus x, and that's the series k equals 1 to infinity of negative 1 to the k plus 1, x to the k, all over k. Right? So ln of 1 plus x is equal to this series. This one has kind of a strange interval of convergence. It's true for x equal to 1, but also in between negative 1 and 1. So if I'm looking at this value ln of 3 halves, notice that ln of 3 halves is exactly 1 plus 1 half. Right? Why did I write it like that? Well, if I plug x equals 1 half into this equation, or into this identity, I'll know exactly what series, right, what infinite series converges to this. So ln of 1 plus 1 half should be equal to, right, the series k equals 1 to infinity, negative 1 to the k plus 1. I'm going to put 1 half in for x over k. So here we see ln of 3 halves is equal to, right, the series k equals 1 to infinity, negative 1 to the k plus 1 over k to the 2k. Right? So now read this equation right to left. This says that this series right here converges to 3 halves. So not only do I know that it's convergent, I know exactly what it converges to.